This is Dr. D. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is work done by the spring. The spring is the device. When it is strained, it will undergo some displacement due to the compression or the elongation. Then later it will come to its equilibrium position. Here example I am taking, the spring is there now. Here it is now, the shown in figure now, the spring. The force is applied just in the direction of right hand side, that elongation is taking place. Assume x is the displacement of the spring now. Therefore, the spring exerts equal force as well as opposite force on the body that compress the or stretches it. That is the elastic potential energy stored, which is equal to the force times the distance of the movement of the body. This potential energy is stored in the spring by virtue of its position, which is depends on the spring constant and the distance stretched. The potential energy stored within the spring is given by minus half of k x square now, where k is representing the spring constant, x is the distance travelled. Generally depends upon when the force is applied, that is the force increases, later it comes to equilibrium position. Hence we have to consider only the average force, that is 0 plus f by 2 we have to take it. That is the force, average force multiplied by the displacement of the spring now. So average force is equal to, it is given by force is equal to k into x, where kx is representing the force which is acting on the body to elongate it, and k is representing the spring constant, and x is representing the distance deformed in the direction of applied force. Since the spring is now the force acting in opposite direction to which the displacement is taking place, and so potential energy is given by minus half 1 by 2 kx square or minus 1 by 2 kx square now. When the spring is stretched by external force, the work done by the spring is equal to W into 1 by 2 kx square now, where k is the force constant of the spring. Sometimes it is also called the spring constant. X is the extended or stretched of the spring. That is, when the external force is applied on a spring, the length of the spring is extended certain amount. The amount of extension is directly proportional to the force applied. Hence, the force is given by F is equal to, you can take it as k into x, where k is representing the spring constant and x is representing the amount of spring extended or stretched length. Hence, the amount of work done, it is defined as the product of the average force and the displacement. Here, when the force is applied, it is a more, afterwards it is gradually just decreases now. Example I am taking here now. Here the spring is there. The force when it is applied to compress it now, initially it is a more, and when it is a compressed certain length, it comes to equilibrium position now. Does it 0 now? Hence, we have to consider only the average force. The average force is equal to 0 plus f by 2, where f is equal to kx already we have taken, k is known as a proportional constant. Hence, work done is equal to force into distance now, that is 1 by 2 into kx into x square, hence it is equal to W is equal to work done is equal to 1 by 2 kx square. By using integration method, let dx is representing the small displacement of the spring when the force is F is applied. Hence, the work done is given by the product of force and the distance. Hence, the small work done on the spring is given by, because of application of external force, dW is equal to F into dx, where F is the force applied to stretch the spring. Now, the elongation produced in the ideal spring is directly proportional to the spring force. Now, hence, F is equal to, we can take it as minus kx now. The total work done in stretching the spring from the intervals 0 to x is obtained by integrating from 0 to x to get the total work done on the spring now. So, substituting F is equal to minus kx, it is equal to W is equal to 0 to x minus of kx into distance mode is equal to dx when we are considering. Since k is the constant, spring constant, when we are taking that k is the outside now, minus k, the remaining is 0 to x dx. On integration to minus k into x square by 2, limits are 0 to x, hence it is equal to 1 by 2 k x square. Here the work done by the external force on the spring is given by minus of 1 by 2 k x square now. Since the energy is the capacity to do the work now, the work done is always stored within the spring as a potential energy. Hence, the potential energy stored within the spring is given by U is equal to minus of 1 by 2 kx square, which is equal to the capacity to do the work. Okay, based on these equations, we are taking yes, small problems. Find out the potential energy of the spring. Having spring constant as 200 Newton per meter and the displacement is 0.8 meters now. Here within this problem, so the given parameters are now spring constant is given now. Generally, it is represented as K. K is equal to 200 Newton per meter. The displacement is given x is equal to 0.8. And so, the potential energy of the spring is given by 1 by 2 into kx square or 1 by 2 into k is equal to 200. The displacement is 0.8, which is equal to 64 joules. Okay, in the second problem, the spring constant of a stretched string is 15 Newton per meter. That means here k is equal to given 15 Newton per meter. And the displacement is 20 centimeters. Compute the potential energy stored in the stretched string now. Here x is given 20 centimeter. We are converting that values into meters, which is equal to 0.2 meters. The potential energy is equal to 1 by 2 k x square. It is equal to 1 by 2 into 50. It is equal to 0.2, which is equal to 1 joules now. We attached one more problem. We attached a spring to a board and use 3 joules energy to stretch the spring 99 centimeters. What will be the value of the spring constant using spring potential energy formula? The energy stored within the spring is given by 3 joules now. So it is equal to 3 joules. The displacement is given 99 centimeters, which is equal to 0.9 meters, 0.99 meters. The potential energy is given by the equation 1 by 2 kx square. Rearranging this equation as now k is equal to 2 into potential energy divided by x square. From this relation we got to 2 into 3 divided by 0.99 whole square, which is equal to 6.122 Newton per meter. This is known as spring constant. A truck of mass of 50 newtons traveling at 1.6 meters per second impacts with a buffer of a spring which compresses 1.25 mm per kilonewtons. Find the maximum compression of the spring. The mass of the truck is given 15 newtons is given now, 15 tons. Mass of the truck is equal to m is equal to 15 tons now. The velocity of the truck is given 1.6 meters per second. Spring constant is equal to 1.25 mm per kilonewtons is given. So let x is equal to maximum compression of the spring in mm. The kinetic energy is equal to, it is given by 1 by 2 mv square, which is equal to, since mass is given, velocity is also given now, 1 by 2, 15 kilonewtons into 1.6 whole square, which is equal to 19.2 kilonewton meter, or it is equal to 19,200 kilonewton mm. The compressed load is equal to given by x by 1.25. It is equal to 0.8x now. That is f is equal to, we are having f is equal to kx. By using the equations, we are having just k is equal to f by k by x now, which is equal to k is equal to, is given by here the load per unit length. It is equal to, that is k is equal to 1 by 1.25. That is the force per length, unit length required, which is equal to 0.8 now. Hence we have taken that is equal to 0.8 as a spring constant, and x is nothing but the distance. It is a mole now. It is equal to 0.8. The work done in the compression of the spring is equal to average compressive load multiplied by the displacement. So the force is given by, since we are considering x is the distance, the deformation of the spring, that is the taking place because of application of the load. So average force is equal to 0.8x by 2 into distance travel, which is equal to 0.4 x square kilonewton meter now. But the work done is nothing but, it is the capacity, energy is nothing but capacity to do the work. Hence work done is always equal to the kinetic energy or potential energy stored within the object. By equating these two equations, that is in equation number 1, the kinetic energy of this truck is given by 19,200, which is equal to 0.4 x square. X square is equal to, we got it 19,200 divided by 4, which is equal to 48,000, or x is equal to 219 mm now. So if you know the value of K now, we can determine the amount of work done on the spring or by the spring. So sometimes, depending on the requirements, the springs are connected in series as well as the parallel also now. In series, K1 and K2 is representing the stiff constant of the two springs. then the total spring constant for the combined springs is given by, that is k is equal to, it can be written as k1 plus k2 now. So after determining k, the value of potential energy that is stored within the spring, it can be determined by using the equation 1 by 2 into k x square, where x is representing the displacement of the or deformation of the spring now. Similarly, when the springs are connected in parallel, so we got 1 by k is equal to 1 by k1 plus 1 by k2. By using this relationship, we can determine the equivalent spring constant for this parallel springs. After determining k values, that is spring constant for the system of springs, we can determine the amount of energy that is stored within the object or the capacity to do the work now. So F is the force that is developed because of the displacement of x. From undeformed position, we got F is equal to k into x. If you know the k values, we can determine the force that is exerted. After knowing force, we can determine the work done or the potential energy stored within the spring now. Okay, work done by the spring is given by now. That at any instant the displacement is dx. The work done by the spring force F, that internal energy that is stored, that potential energy stored is given by, which is the equivalent to the work done. The work done is equal to minus of F into dx, or F is equal to minus k x into dx. Since a negative force is nothing but it is opposite directions to the dx now. Hence, work done in the displacement of the body from x1 to x2 position is given by, that is the x1 to x2 integration minus of kx dx, which is equal to 1 by 2 k x2 square minus x1 square now. If the displacement is from the undeformed position, that means that x1 is equal to 0 and x is the displacement, the modified equation is given by u is equal to minus of 1 by 2 k x square. These two equations, one is nothing but, the first one is representing 1 by 2 k into x2 square minus x1 square. It is the potential energy stored within the object when the spring is stretched from x1 position to x2 position. That is the deformed distance of x2 minus x1. Sometimes when it is unstructured condition, undeformed condition, when we are taking, that is x1 is equal to 0. If x is representing the deformed position, deformed length, then the modified equation for the internal energy stored within the spring is given by minus of 1 by 2 k x square. If deformed spring is allowed to move to its normal positions, then k is equal to k into x square now. Okay, just one problem we are taking now. A wagon of mass 50 tons start from the rest and travels 30 meters down at 1% grade and strike a post with a bumper spring as shown in figure. If the rolling resistance of the track is 50 newtons per ton, find the velocity with which the wagon strikes the post. Also find the amount by which the spring will be compressed. If the bumper spring compresses 1 mm per 20 kilonewtons force. Here the given data is the mass of the wagon is given 50 tons now. mass of the wagon 50 ton, start from the rest. That means the initial velocity of the wagon is 0. That is mu is equal to 0. And it travels 30 meters down. That is from the inclined plane is given 30 meters down it is moving now. So the distance traveled is equal to 30 meters, and at 1% grade, that is the inclined plane is having 1% now. That is 1:100 now. That means if we go then nothing but 100 mm. So it is having the grade is 1 now. Generally it is equal to sin theta is equal to 1 by 100, which is equal to 0.01. The rolling resistance of the track is 50 newtons per ton is given. Rolling resistance, generally it is treated as the frictional force now, or it is called tracking force now. But the total weight of the wagon is given 50, and so the total resistance is given by 15 to 50, which is equal to 2500 newtons or 2.5 kilonewtons. Bumper spring constant, that K is given now. It compresses 1 mm per 20 kilonewton force now. That is spring constant is given by force per unit length, hence it is equal to spring constant is equal to, we have taken that is 20 divided by kilonewtons divided by that is 1 mm. It is equal to 20 kilonewtons per meter. This is known as the spring constant now. So this is the given data collected from the problem. Now the required data is find the amount by which the spring will be compressed now. Find the velocity with which the wagon strike the post. These two are required now. Okay, first one we are taking the velocity with which the wagon strike the post. So let V be the velocity with which the wagon strike the bumper, that is a spring now, or sometimes it is also called post now. Here, when I am drawing the free body diagram of this one, here it consists of two types of forces now. And frictional force is there now, since it is moving in upward directions, downward directions. The frictional force is acting upward directions, and it is equal to normal reactions. So in this case, since the wagon is traveling in downward directions now, this mg sin theta, the component of weight, that is the W, which is parallel to the inclined planes, it is called sliding force. It pulls the wagon to move in downward directions. Hence, the gravitational pull is equal to, it is given by mg sin theta, which is equal to 50 into 9.8 into sin theta. This is equal to theta values mg sin theta now, which is equal to 4.9 kilonewtons. This force is mainly caused to move the wagon in downward directions. Hence, the total force which is responsible to move the body down the plane is given by the resultant of sliding force as well as the tractive resistance now, which is given by 4.9 representing the gravitational pull and 2.5 is representing the resistance force now. So which is equal to 2.4 newtons kilonewtons, which is acting in downward directions. It is responsible to move the body down the incline. So the net force responsible for the moving the wagon is equal to 2.4, which is equal to, we can write it m into a now. where A nothing but representing the acceleration in which the body is moving in downward directions. M is representing the mass of the wagon, so which is equal to 50 into A now. So from this relations we got A is equal to 2.4 divided by 50, which is equal to 0.048 meter per second. This is known as the acceleration which the body is moving down the plane now. So in order to find the final velocity with which the wagon strike the post, we can use the equations v square minus u square is equal to 2as, because t is nothing but not provided. The time taken to travel a distance of 30 meters is not taken. That is, here the words are given. Since it is coming from the rest, initial velocity is equal to 0. Final velocity we have to determine now. The distance traveled is equal to s is equal to 30 meters is given. By using the equations v square is equal to u square plus 2as, from this relations, here we got initial velocity is equal to 0. That is, we got 0 plus 2 into A is equal to, already we determined, which is equal to 0.048, and S is equal to 30 meters is given. From this relationship we got, that is V is equal to, V square is equal to 2.88 and V is equal to 1.7 meter per second. That means by using the relationship we are determine the velocity with which the wagon is striking the post now. Here just we are using the two equations. One is F is equal to M into A now, where F is representing the resultant force which is responsible to move the wagon in downward directions, which is equal to the difference values of mg sin theta, that is the sliding force, or sometimes it is also called pull force, and the friction force which is opposing the difference of these two values is responsible to move the wagon in downward directions, which can be written as M into A. We calculated that A values. After that, by using the relations V square is equal to U square plus 2as, we determine the value of final velocity with which the body is striking the post now. The amount by which the spring will be compressed now. Let x be the amount by which the spring will be compressed now, taking mm dimensions now. The kinetic energy of the wagon is equal to 1 by 2 mv square now. When before it is striking, it is having velocity v is equal to 1.7. That means after traveling a distance of 30 meters, its velocity is given 1.7 meter per second. Hence, it is equal to 1 by 2 mv square means 1 by 2. Mass is equal to 50 newtons given 1.7 whole square, which is equal to 72.25 kilonewton meter now, which can be written as now 72,250 kilonewton in mm now. So the compressed load is equal to now given by, already we have taken the spring constant is equal to, if x is equal to the distance moved now, and k values is given, which is equal to 20. So 20 into f is equal to, that is nothing but the total force which is acting or responsible for compress the spring now. So work done in the compressed spring is given by average load multiplied with the displacement. So 0 plus 20x by 2, or it is equal to 20x by 2 into x now, or it is nothing but equal to 1 by 2 into kx square now, where k stands for the spring constant, which is equal to here now 20 kilonewton per mm, and x is nothing but the displacement of the spring. So by using this equation, we determine this value is equal to 10 x square kilonewton mm. Since the entire kinetic energy of the wagon is utilized to compress the spring, or in other words, this kinetic energy is converted into the potential energy within the spring. Hence, equating equation 1 and 2, we got to 10 x square, it is equal to just from the second equation to the first equation is given 70,250 and equating these two, x square is equal to 720 7,225 or x is equal to 85 mm. That means the spring compresses a distance of that is 85 mm when the wagoner receives the force. Okay, this is our required answer now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.